Based on the concepts of quantum mechanics, we can study the wave functions in hydrogen-like atoms. There are two particles in a hydrogen-like atom, the nucleus and the electron. Both are quantum particles. In principle, we must study them all together. However, under Born-Oppenheimer approximation, the motions of nuclei and electrons can be separated. Here, we only need to consider the motion of the electron. It is because the nucleus is much heavier than the electron. So, the motion of the nucleus is much slower. We can regard it as stationary. The potential energy of the electron depends only on its distance from the nucleus. It can be expressed with either spherical coordinate system or Cartesian coordinate system. Obviously, the expression in spherical coordinate system is much simpler. Therefore, the spherical coordinate system will be used for later discussion. We know that, in Cartesian coordinate system, the coordinates are x, y and z. In spherical coordinate system, the coordinates are r, theta and phi. The relationship between x, y, z, and r, theta, phi is shown in the figure below. In spherical coordinated system, the wave function is a function of r, theta and phi. Here, I skip the process of the solution of the Schrödinger equation. The result wave function is the product of the radial function r and the angular function y. The angular functions are spherical harmonics. N, L, and ml are quantum numbers. We can use them to denote a state. The following 4 slides are extremely important in general chemistry. Please make sure you remember and understand the key concepts in them. N is called the principal quantum number. It is a positive integer, say, it can be 1, 2, 3, 4, etc. The principal quantum number determines the mean distance between the nucleus and the electron, and the energy of the state. Each principal quantum number corresponds to a shell. The shells also have their notations. For example, the shell whose principal quantum number is 1 is the K shell. The shell whose principal quantum number is 2 is the L shell. The shell whose principal quantum number is 3 is the M shell. For higher principal quantum number, the shell notation goes on in alphabetical order. In hydrogen-like atoms, the energy of a state depends exclusively on its principal quantum number. The expression of energy is shown below. The ground state is the state whose principal quantum number is 1. Its energy is about -13.6 eV. You can find that the energies are exactly the same as calculated by the Bose model. So, they also perfectly reproduce the line spectrum of hydrogen. However, the line spectra of multi-electron atoms cannot be calculated by this equation because of the interaction between the electrons. L is the azimuthal quantum number. It is an integer from 0 to n-1. The azimuthal quantum number determines the shape of the wave function and the magnitude of the orbital angular momentum of the state. The relation between the azimuthal quantum number and the angular momentum is shown below. You can find that the expression of angular momentum is different from Bose model. Experiments have proved that this expression is correct, while Bose expression is wrong. That is why Bose model is called old quantum theory, even if it gives the correct energies. In a shell, each azimuthal quantum number corresponds to a subshell. The subshells have their spectroscopic notations. The subshells whose azimuthal quantum number are 0, 1, 2, 3 are S, P, D and F subshells respectively. ml is the magnetic quantum number. It is an integer between -L and L. The magnetic quantum number determines the projection of orbital angular momentum of the state on the z-axis. The relation is shown below. In the subshell, each magnetic quantum number corresponds to an orbital. For example, when the azimuthal quantum number is 0, the magnetic quantum number must be 0. This orbital is the s orbital. When the azimuthal quantum number is 1, the magnetic quantum number can be 0. This orbital is the pz orbital. The magnetic quantum number can also be ±1. They correspond to px and py orbitals. When the azimuthal quantum number is 2, there are 5d orbitals. When the azimuthal quantum number is 3, there are 7f orbitals. For general chemistry, you should be familiar with the s and p orbitals. Each electronic state in the hydrogen atom is an orbital. We can use the principal quantum number and spectroscopic notation to denote each orbital. For example, when the three quantum numbers are 1, 0, 0, the orbital is the 1s orbital. Its wave function is shown below. The constant A0 is the Bohr radius. It is the radius when n equals 1 in Bohr's model. And it is the typical size of atoms. You can see that the wave function of 1s orbital is independent of the direction. So, the 1s orbital is spherically symmetric. The wave function decreases exponentially with the distance from the nucleus. The state with quantum numbers 2, 0, 0 is the 2s orbital. It is also independent of the direction and is spherically symmetric. In fact, all the s orbitals are independent of direction and are spherically symmetric. In contrast with the 1s orbital, the 2s orbital has a node. In three-dimensional space, a node is a surface where the wave function is 0. The node of 2s orbital is a sphere. Additionally, the signs of the 2s orbital inside the node and outside the node are opposite from each other. The 3s orbital has two nodes, and the wave function has opposite signs on the two sides of each node. The wave functions of the 2p orbitals are shown here. There are characters in these functions. First, the radial parts of the functions are identical. Second, they are direction dependent. They are not spherically symmetric. By using the relationship between the spherical coordinate system and the Cartesian coordinate system, we can find that the wave functions are cylindrically symmetric in x, y, and z directions respectively. The shapes of the 2p orbitals are shown here. We can find that all the 2p orbitals have the same shape, but different orientations. The red and blue colors represent the positive and negative signs of the wave functions. In each wave function, between the positive and negative branches, there is a node. In 2p orbitals, the nodes are planes, so they are also called nodal planes. Here are the shapes of all the 3d orbitals, and one of the 7,4f orbitals. They are not discussed in general chemistry, but you had better to know them, because they will be very important in inorganic chemistry. In this table, I summarized all the important information about hydrogen atom orbitals. Note that the number of orbitals in a subshell is 2l plus 1. For instance, when L equals 0, 1, 2, or 3, the number of orbitals in the subshell is 1, 3, 5, or 7 respectively. The number of orbitals in a shell is n square. For instance, when n is 1, 2, 3, or 4, the number of orbitals in the shell is 1, 4, 9, or 16 respectively. Please try to prove these relations by yourself. The last property of electron to discuss is its spin. It was discovered in Stern-Gerlach experiment. In the experiment, a beam of silver atoms from a furnace traveled through an inhomogeneous magnetic field. They split it into two beams. One deviates towards the stronger field. The other deviates towards the weaker field. We know that magnetic dipoles experience force in inhomogeneous magnetic field. Stern-Gerlach experiment suggested that there are two types of silver atoms carrying opposite magnetic dipoles. Orbiting charged particles produce magnetic dipoles, so the magnetic dipoles in silver atoms were considered to be caused by the motion of the electrons in them. However, as shown in the last slide, the orbitals only carry odd numbers of angular momenta. Thus, two angular momenta from Stern-Gerlach experiment cannot be explained by the motion of electrons. The Stern-Gerlach experiment proved that there is another quantum mechanical property which is independent of the motion in the space. It is called spin. The spins carry angular momenta and magnetic dipoles. There are two quantum numbers related to the spin. The first is the spin quantum number. It determines the magnitude of spin angular momentum. It is the analog to the azimuthal quantum number. The spin quantum number of electron, proton, and neutron is half. The spin quantum number of photon is 1. The second spin quantum number determines the projection of spin angular momentum in z direction. It is the analog to the magnetic quantum number. The second spin quantum number of an electron can be half or negative half. They are usually denoted by the up and down arrows. The spin can be understood from the picture of rotating charged particles. But it is a pure quantum mechanical property and is totally different from the classical rotation.